Welcome. My name is Randy Ellis. In this session, we'll review prerequisites for nonlinear data analysis, and this part will be linear data analysis. The main concepts for this session are labels that are provided to us by a user. These partition observations for us, and supervised learning is how to use the labels to learn from the data. The basic method that we'll use is hyperplane separation, and this is often implemented in terms of logistic activation or logistic regression. So in machine learning, labels are categorical variables for an observation, and they're categorical, so we can't, for example, scale them. They are what they are, and what they do is they partition our data into subsets that the user or the providing system thinks are important. The simplest case is binary labels for two subsets, so something is in or not in. For neural networks, these are often represented or encoded as 0 or 1, and for other frameworks, they may be encoded as -1 or +1. It's important to read your source to figure out how they are denoting the binary labels, because often this method of denoting it is encoded deep inside the mathematics of the learning system. So we have to read these carefully. So for vectors, we'll think normally data are given to us as observations. Here I'm just going to refer to them as vectors because that's often the way that neural networks will refer to them. So for a given hyperplane, which we're denoting by this block H, the pseudo distance is just the dot product of our data vector and the hyperplane normal plus the offset, the scalar offset for the hyperplane. And to avoid this affine computation and turn it into a linear computation, it's very common to augment the data and augment the hyperplane. So augmented hyperplane means we go one dimension higher and we say that our hyperplane normal is W and then the scalar value is B, and we'll append that or augment it into a vector that's one size higher. And similarly, we'll use a hat over our data vector to indicate we've taken the data vector and we've appended a 1 to it. What that means is we can now compute a pseudo distance. So the pseudo distance is going to be a positive real value if the data vector is on the positive side of the hyperplane. It will have a negative value if it's on the negative side of the hyperplane, but it's a pseudo distance because it doesn't really measure the projected orthogonal distance of the data point to the hyperplane. And now we can compute this as a value u, and this is now simply taking the augmented data vector transpose times the augmented weight vector, which is a different way of doing the dot product. So a simple artificial neuron is implemented, and what it normally does is it quantizes the data to match the labels. Because our labels coming in a neural network are 0 and 1, we'll quantize to match it. This is called an activation function, and this is a transformation from a real number, so it's like a pseudo distance u or a score z, and we map it to the labels. So to map a real number to 0 and 1, it's common to use the Heaviside step function denoted by capital H. And this is 0 if the input argument is less than 0, and it's 1 if it's greater than or equal to 0. And note that in some contexts, this greater than or equal will be turned to a less than or equal here. So you have to read your sources carefully for this annoying detail. So a simple neuron model can be this, is that the neuron will output a 0 if the pseudo distance of the data vector is negative, and it will return a 1 if the pseudo vector is non-negative. The pseudo distance is non-negative. So neural networks, this quantization was difficult to work with early in neural networks, and Rummelhart and colleagues developed some nonlinear activations of the hyperplane. So the idea was they wanted the data to flow from the left through the middle to the right, and they wanted multiple layers of artificial neurons that they called a neural network. So on page 9 of this foundational article, they note that they use a logistic activation function, which we're showing as a little script. So let's get into that script in a little more detail. So semilinear activation is often called the sigmoid activation function or the logistic activation function. It's called a sigmoid because it has an S shape. And for our augmented data and weight vector, the computation of it is this. We take the pseudo distance, negate it, exponentiate it, add 1, and then divide that into 1. And this is a smooth approximation to the Heaviside function. It's differentiable, although the differentiation is a little bit annoying. And the derivatives asymptotically approach 0. So as a data point is very far from the hyperplane on the negative side, it will be 0. The derivative will be 0, and it will be also 0 as it's very far away on the positive side. So we can now, for an artificial neuron, the next thing is what we want to do is something similar to what we did in linear regression, which is we want to minimize some error. And that means we have to measure the error. So the residual error of classification is if the label is denoted as Y, which is quite common, and our logistic activation is now a score, Z, which is going, in this case, from 0 to 1, we'll say that the residual error is the difference between the label and the score. So this looks sort of like what we had for residual error in previous material. There are two common ways of managing this residual error, and by managing I mean combining residual errors from a whole bunch of data. So here we have data vectors, combining them from a whole bunch of data into a single number that we can manage. And the two ways are, we can say that the ith error is the square of the residual, so that is along the lines of what we did for linear regression, or we can use what's called the negative log measure. And what that means is if the label is 0, we perform this computation. If the label is 1, we perform this computation. So we can either use a squared error objective or a negative log objective. And what we can do is we can plot the errors to visualize the effects. So suppose that we have a sigmoid, and we're going to try to measure the net error. So the net error will go from a maximum of 1, and then it will drop down, and then it will return back. So the important things to note are that this is monotone, it's locally monotone, and it has a single global minimum. And that will be important when we get into actually performing computations in nonlinear data analysis. The other way to measure it is the total negative log error. And here the sigmoid, now we've changed the scales of it, but this is the same sigmoid. For negative log error, unlike the squared error, the squared error was asymptotically 1. This is asymptotically infinity, as we have misclassification errors, and it has a single global minimum. And now this one is locally monotone, and it turns out to be convex. So how can we learn the weights given data? Well, to date, using the logistic activation function for artificial neurons or doing logistic regression, I don't know of any closed form solution. And we do numerical approximations. So the idea is we'll minimize residual error, and we'll measure residual error in one of these two ways. There are a lot of approximation algorithms for these, and this gives us bridges to many other areas. Nonlinear data analysis is the intended bridge that we're going from this prerequisite material, but we can also go into some numerical optimization that is more mathematical, or we might go into neural networks, which are used in general data analysis. I'll note also that in statistics, this is another form of logistic regression. So how can we summarize this session? Well, what we can do is we compute the error for each observation based on the weights that we've learned, and we can then add up the weights, and it will turn out that these errors are nonlinear in the weights. So the numerical methods that we can use are, if we're using a squared error, we may want to use a steepest descent method. Logistic regression, we may want to use a maximum likelihood method.